A complex machine is able to operate effectively as long as at least 3 of its 5 motors are functioning. If each motor functions independently for a random amount of time with density function f of x equals x times e to the negative x, when x is greater than 0, computes the density function of the length of time that the machine functions. To illustrate the approach to this problem, we study a few numerical cases. Let capital X sub I be the amount of time that the ith motor functions, where I is from 1 to 5. Question: how long does the machine function in each of the following cases? In case A, capital X1 equals 5, capital X2 equals 10, capital X3 equals 7, capital X4 equals 9, capital X5 equals 15. That is, at time 5, the first motor stops running. At time 7, the third motor stops running. At time 9, the fourth motor stops running as well. Also, at time 9, only 2 out of these 5 motors are running, namely the second and the fifth motor. Therefore, there is not enough motors running for the machine to operate effectively. In other words, the machine must stop operating as well. Thus, the answer for this question is 9, the time when the fourth motor stops running. Let's look at case B. At time 7, the fourth motor stops running. At time 8, the second motor stops running. At time 11, the first motor stops running. And at the same time, the machine will stop operating as well, because there are only 2 motors working normally. Therefore, the machine would work up to time 11 in this case. In terms of order statistics, both of those 2 stopping times are equal to the third order statistic. If we contemplate over our findings, it's easy to come to our following conclusion. The length of time that the machine operates equals the third order statistic. Now, our goal has been transformed to finding the probability density of the third order statistic. Let's recall the formula for the probability density of the third order statistics. If you'd like to review the derivation of this formula, you could refer to one of the previous videos. I will put the link in the description. To implement this formula, we need to find the cumulative distribution of the random variable, which is the integral from negative infinity to x of the probability density function. Recall that our probability density function is equal to e times e to the negative t when t is greater than 0. So our integral is converted to this format through calculation, such as the integration by part. We conclude that the outcome is equals to 1 minus e to the negative x times x plus 1. Consequently, 1 minus capital F of x is equal to e to the negative x times x plus 1. Putting things together, we have the probability density for the third order statistic given by the following expression. The constant term could be reduced down to 30. And the term capital F of x to the second power is just 1 minus e to the negative x times x plus 1 squared. And the term 1 minus capital F of x to the second power is just e to the negative x times x plus 1 squared. And lastly, we just have the probability density for the random variable capital X, which is given by x times e to the negative x And the domain for this function is x greater than 0. And as we have observed, this function is the same as the probability density for the length of time that the machine operates effectively. And this completes our problem.